Dear students, Namaskara. Hope you are all studying the physical concepts which I described in my previous videos. This video is the continuation of the topic of dielectrics. In this lecture I am going to derive an expression for the internal fields in the dielectric materials, especially in the solid dielectrics and liquid dielectrics. Then finally we will generalize it for all types of materials including the gases. Let's see what is the internal field or the local field in a solid or the liquid dielectrics. By definition, it is the electric field at the site of an atom or a dipole, that is the sum of the external field applied and the electric field due to surrounding dipoles. That means in a dielectric material there are infinite number of atoms or dipoles. When we apply some electric field to that material, there will be the polarization. When polarization occurs, the dipoles will be formed within the material, and due to the dipole itself an electric field is developed at their site. They are the charged particles. When there is a charge, there will be a field of influence which is known as the electrostatic field around it. So an electric field is developed in the vicinity of a dipole. So that at the site of the dipole now there are two electric fields. One is the field that we have applied externally, let us take it as capital E, and the field developed by the dipoles themselves. So that the total electric field, that is the sum of the external electric field capital E and this E dash, the field due to the dipoles, gives you the internal field. Now let us look into a derivation wherein we are going to derive the expression for the electric field, that means the internal electric field at a given point within the dielectric material. This diagram shows an array of the dipoles. X is one dipole. On either side of the same there are two dipoles, A1 and A2, and next to this position B2, C2 towards right and B1, C1 towards left. So for the mathematical simplicity we are taking one row on which the dipoles are arranged. Let us assume that the distance between the dipoles is constant, which is equal to the small letter d. That's why it is called one-dimensional array of dipoles in presence of an electric field E. Now in order to have an expression for the electric field at the site of this particular dipole, let us say X, consider another diagram in which the dipole is shown to have two charges. This can represent one charge, this is the other charge. This may be negative charge or that may be the positive charge. The distance between them is not d here, because the distance between the two charges within the dipole in our previous lecture was taken to be d, but here in this derivation this d is the distance between the two dipoles, not the distance between the two charges. Okay. And if you consider any point in the vicinity of this dipole, let us say P at a distance r, at that point you can have the electric field capital E which is resolved into two components, E theta and ER, radial component and angular components. There are expressions for this ER and E theta which I am not going to derive here. This expression for the electric field ER is going to be mu cos theta divided by 2 pi epsilon naught R cube, and E theta is mu sin theta divided by 4 pi epsilon naught R cube. Here you already have understood what R is. Theta is the angle made by the line joining this point from the center of the dipole with the axis of the dipole, that is theta. If you consider this dipole, that is X, and electric field at that point, at the point where X is located, due to the neighboring dipole A1, then the distance is said to be equal to D, and the angle theta is 0 degree. If you are considering the dipole A1, due to which an electric field is established at a point where X is located, the distance of this X is shown to be D here. So in the next part, since we are taking the distance between the dipoles as D, here it was represented as small letter r, now they are equal to each other, since we are taking the dipole A1 whose electric field is to be determined at the point X. So theta becomes 0, hence this expression ER is equal to mu divided by 2 pi epsilon naught R cube, because cos 0 is equal to 1. Similarly, if you put theta value 0 here, sin 0 is 0, so which gives you E theta value equal to 0. The field at the site of the dipole X, this one, is the sum of the radial component and the angular component, which is equal to mu by 2 pi epsilon naught d cube, as I described in the previous slide. Field due to the dipole A2, this one, has the same magnitude because it is at the same distance and on the same axis. Therefore, the magnitude of the electric field due to A2 at the location of X remains the same. Therefore, the total electric field at the site of the dipole X can be taken as 2 times this value, mu by 2 pi epsilon naught d cube. Here mu is the dipole moment, so that on cancelling these two, you will get only mu by pi epsilon naught d cube. This is the total field E1 at the site of X due to both A1 and A2. Now let us look into the field at the same location due to the dipoles B1 and B2. The distances are doubled, that is the only difference, so that the angle remains the same since they are all on the same row. Therefore, the electric field E2 due to the dipoles B1 and B2 at the site of X is mu by pi epsilon naught 2d whole cube, because the distance was d in the earlier case, that was the distance between the atoms A1 and X or A2 and X, but now we are considering the dipoles B1 and X. The distance between them is 2d, 2 times d, that's why 2d is mentioned here. Similarly, the field at the same location again due to the other dipoles C1 and C2, which are at a distance 3d from X, is therefore E3 is equal to mu by pi epsilon naught 3d whole cube. Hence, the total field due to all dipoles lying on the array must be the sum of the fields due to all individual dipoles. If there are n dipoles, you can have n number of terms here. If there are infinite atom dipoles, then infinite number. That's why it can be expressed as mu by pi epsilon naught d cube summation from n to infinity, 1 to infinity n cube. But from the infinite series we get one information that the summation of 1 by n cube, where n is a positive integer, is close to 1.2. That is substituted here. Now, as I defined earlier, the internal field is the sum of external field and field due to dipoles. External field is taken as capital E, and now field due to the dipoles is determined. The sum of the two fields gives you the internal field. In the previous lecture I had talked about the dipole moment and the polarizability. Their relation is here. Since polarizability is the dipole moment per unit electric field, here the total electric field is internal electric field EI. Therefore we write mu is equal to alpha E into EI, where alpha E is the electronic polarizability. So that in terms of this electronic polarizability and the internal field, we write mu as alpha E into EI. So that now you are having two terms, EI and this term multiplied by EI. So that EI is taken outside this common term now, and E is kept on the right side. On simplifying, you will get the expression for EI, which is equal to capital E divided by 1 minus 1.2 alpha A pi epsilon naught d cube. Hope you know that epsilon naught is the permittivity of free space. Here we have assumed that the permittivity of the medium which we have considered is 1. This is the expression for internal field at a dipole in case of one-dimensional array of dipoles in solids and liquid dielectric materials. But for a three-dimensional structure, what would be the equation? For three-dimensional structure, it has been shown that 1 by d cube is close to the number of dipoles per unit volume. Here capital N is representing the density of dipoles, number of dipoles per unit volume. Here you are having 1 by d cube. It is dimensionally 1 divided by meter cube, and N is also having the same dimension. 1 divided by meter cube is the unit. Therefore dimensionally the two terms are the same. So in the place of 1 by d cube, in the expression for the electric field, internal electric field, either in this equation or in this equation, in the place of this 1 by d cube, we have to express capital N. And 1.2 divided by pi in the equation, here 1.2 divided by pi, you can have a symbol, that is gamma. So on substituting those, we will get this expression, EI equal to E plus gamma capital N alpha EI by epsilon naught. Here this is the expression for the internal field in the case of a three-dimensional structure. In simple form, this can be expressed as E plus gamma P divided by epsilon naught. P means it is N alpha E into EI, because alpha E into EI is nothing but the dipole moment. And we had learnt in the previous lecture that the polarization P is equal to N alpha E into capital E, because it is polarization is the dipole moment per unit volume. Dipole moment per unit volume, mu divided by V. It was the expression told in the previous lecture. Now let us look into the other term which is known as the Lorentz field. It is defined as the internal field in three-dimensional array of dipoles in cubic structure. It is only in the case of cubic structure. The equation which we derived earlier is a general one. Now we are looking into the cubic structure. So that internal field for the three-dimensional array of dipoles in the cubic structure of a material is known as the Lorentz field. It is given in terms of gamma equal to 1 by 3. Lorentz has shown in a theory that gamma is equal to 1 by 3 for the cubic structure. So that on substituting gamma value as 1 by 3 in the equation which we derived earlier, we can write EI is equal to E plus P by 3 epsilon naught. So this is known as the Lorentz field or Lorentz internal field. Now we are coming to the conclusion level of the derivation. We have learned that the internal field in the case of solids and dielectrics is the expression which I shown earlier. This is the expression for the internal field in the case of solids as well as liquids. But now we have to understand what would be the situation in the case of the gases. In case of gases, you know that the distance between the molecules or the atoms is very high as compared to the distances between the atoms and or the dipoles in case of solids and liquids. Or mathematically, the D can be taken as infinity for gases. Because of that reason, in the equation of internal field, we will get the second term equal to 0. Because you can observe here that in this equation, you can observe that if D is equal to infinity, the second term becomes 0. Therefore, EI is equal to only E. That is what has been shown here in the last slide. So what do we understand? In the case of gases, internal field is just same as the external field which we have applied, because the electric field established by one dipole is 0 at the site of its neighboring dipoles because of the long distance.